Hello there and welcome to a brand new lesson. This is How Beyond Numbers, where we learn maths the easy way. In this lesson, we'll be solving questions on strand 1. Strand 1, substrand 1, that is number and numeration system. This topic is made up of modeling number quantities more than a million using graph sheets, isometric papers, and then multi-base blocks. Comparing and ordering whole numbers more than a million and then representing the comparison using greater than, less than, or equal to, and then rounding off, up, and then down whole numbers more than a million to the nearest 100,000, tens of thousands, thousands, hundreds, and then tens, and then rounding decimal to the nearest tenth, hundreds, and then thousands, and then finally expressing decimal numerals to given significant and decimal places. We'll be solving 50 questions, 50 objective questions, but I'll take time to explain so you understand and also apply them in subjective questions as well. My advice to you is that you take your paper, your pen, your notebook, pen, or whatever you want to use to work along, and try as much as possible to pause each time the question is read, and then you'd also work it out before you come and then compare your answers and then learn as we work together. After every 10 questions, I would advise you stand up and then stretch as well, so as to release a little bit of tension or stress. Since this is going to be solving direct questions, if you actually want detailed explanation on what we are about to learn, you can just go to the home page, and in the home page you click here on home. You see, now on the home we have the first one being the popular videos, then we have videos. These are the videos I've released recently. You also have your courses, and then you have numbers. So under numbers, the strand we are about to talk about is this number and then numerals, and also modeling. So we are solving questions on these two. This first one has 13 videos, in-depth videos that you'll be learning on all that we want to do now. And then we also have this one on modeling, which also explains a lot. So here are those on the number and then numerals, and then it even has some questions as well for you to try. Then on the modeling, these are also some. So if, as we solve the questions, you have any question in particular and you actually want to address it to me, or you want me to actually solve a particular strand or set of questions for you, you can always reach me here on my Telegram link. So without much ado, let's quickly look into it. So our first question says, in the multi-base block modeling system shown in the document, how many blocks, that is each representing 100 million, are required to model quantity of 1 billion? So this is trying to tell us that a block is what? 100 million, and we want to arrange a particular number of blocks to give us a billion. So let me write down that parameter here. So we are saying just one block is what? 100 million, but we want to model a billion. You see, so how many blocks do you need? It's very simple. All you need to do is to divide the quantity you want to model, that is the billion, by what? The block quantity. So we are coming to divide. So I'll just put this over here, and then we do our division. So these 3 zeros cancel out to these 3 zeros. These 3 zeros cancel out to these 3 zeros. This takes out this, and then this takes out this. So we are going to get what? A 10. So it simply means that to model the quantity 1 billion, we actually need 10 of the blocks to do that. You see, so that will be B. You see, now I would advise that as we solve, anytime I move to a question, you take time to also pause and then solve it by yourself before you now continue to check your answer. So let's look at the next question. It says, using the modeling system where a flat, just one flat, represents what? A 10 million. How many flats will you need to represent the value of one block? And talking of a block is 100 million. So what do? This is just as we did for the first one. We are going to divide, you see. So writing down our parameters, we have a flat being a 10 million, and then a block being 100 million. So we want how many flats are going to be needed to get what? A block. And what is that going to be? We are just going to divide the quantity or the units that represent what? A block. We are going to divide that by what we have for a flat, just as we did for the previous one. So this cancels this. We have 1, 2, then all these 3 are also taken by this, and then this 0 also takes out this. At the end, we are going to get what? A 10. It simply implies that we are then going to need 10 flats to represent a block. As simple as that. Let's go to our next question. Now the next one says, if you are asked to represent 185 million Ghana cedis using only 200 currency tokens, which calculation correctly determines the number of tokens needed? This is a division question. So if you want a number of 200 cedis, that gives us this particular word currency or this amount of money, then we are just going to do what? Divide, you see. So for the first one here, it says we're actually dividing the 200 by the amount of money. That is not true. For the second one, it says subtraction. That is also not true. Hence, for our third one here, which says division, that is going to be our answer. It says to find the number of tokens, you divide the total amount by the value of a single token. Let's look at our next question. It says, based on the comparison example in the curriculum, which symbol correctly completes the statement? So which symbol are we to put here? Now remember, anytime you want to compare two numbers, we always say you should count the number of what digits they have in there. So for this, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then this on the other hand has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is the first check. Assuming one had a more number of digits than the other, then the one with the greater number of digits becomes the greatest. But since in this case they all have the same number of digits, we now compare the corresponding digits. So what I mean is we are looking at the corresponding place value. We have 5 over here, and then there's also 5 over here. So we go to the next digit. There is a 2 here, and then there's also a 1 here. We end over there. Now for 2 and 1, which one is greater? The 2 is far, far greater. Hence this particular number is greater than what we have over here. So we are in to choose what? Greater than. So the reason is the first number is greater because the digit in the second hundreds of millions place is greater than the corresponding digit in the second number. You see, let's look at question number 5. So in this next question, it says, according to the round up and round down concept explained in the text that is in our notebooks, how should you round 2,846,655 to the nearest thousand using the round up method? So we are actually rounding it up. The number is what? 2,846,655. So when it comes to rounding up, what do? We always identify where we want to round up to. In this case, we are rounding up to the nearest thousands. So we identify the number in the thousands. Now, what we always do is, for rounding up, we always add 1 to that digit in the place value where we are talking about. So we just add 1 to this digit. What do I mean by that? As we add 1 to this digit, we change all we have here towards zeros. So this 5 becomes a 0. This 5 also becomes a 0. The 6 becomes a 0. And then we are now here. So this 6 plus 1 gives us what? A 7. Then the remaining numbers remain just as they are. And this is our rounding up. So the most important thing is you identifying the place value we are talking about, and then you increase it by 1. In that case, our answer is A. This is rounding up requires moving to the next larger number in that place value category, which is what we have over here. Let's look at our next question. It says, if you round the decimal 78.4604783 to the nearest hundredth using the round off method, what is the result? Take note. We are actually working with a decimal here, you see, and it says we should round off. Take note of the off. Now, when it comes to decimal place value system, this here is a 10. That is a 10. Then you just add a th to it, you see. And then this 6 here is 100 with a th. This is 1,000. That is 1,000 with a th. So in this case, we are rounding to the nearest hundredth. This is what we have over here. So rounding to the hundredth, you need to check the number that comes after the 100. That is a 0. So in this case, we say if it is 5 or more, we raise the score. Raising the score simply means we round up. On the other hand, if it is 4 or less, we do what? We let it rest. Let it rest simply means we round down. You see? So since we have 0 over here, 0 is within this column. Hence, we are just going to keep the digits just as it is. So that we have our 78.4. And since nothing is going to happen to the 6, because the decider is what? 0, it remains what? 6. And that simply means our answer is what? C. So it says in rounding off to 2 decimal places, since the third digit is less than 5, the second digit remains unchanged. Let's look at our next question. Now this next one says in the decimal that is 0.360, how many significant figures are present? You see, all we want is the number of significant figures. So for 0.360, we know what significant figures are. First, all non-zero digits are significant. Secondly, leading zeros are insignificant. Third, trailing zeros are significant if they appear after a decimal point. And sandwich zeros are what? Significant as well. So in this case, this is a leading zero. Leading zeros are not significant. Hence, if we want to actually count our significant figures, it starts from here, the 3, 6, and then 0. You see, so this 0 we have here is a trailing zero. It is significant. Hence, we have 3 significant figures. So as you can see, the reason says trailing zeros to the right of the decimal point is a decimal number. In the decimal number are counted as significant. Let's look at our next question. It says we have to round this number to 3 significant figures. Round to 3 significant figures. Now, if we want to round this number to 3 significant figures, then there is a need for us to first of all identify the first significant figure. You see, so in this case, this 0 is not significant. This 0 is also not significant, followed by this is also not significant. Hence, we have our 2, which is significant, 3, which is also significant. Now, we want to end on the third one. But to end on the third one, we need to check the decider, that is 5. So if it is 5 or more, we do what? We add 1 to where we want to end. So in this case, since it is 5 or more, we are going to add 1 to this so that it becomes 5. and this will be towards 3 significant figures. All these zeros we have here are leading zeros, and leading zeros are not significant. Take note of that. So our answer is what? 0.00235. And then it says the first non-zero digit is 2. Counting 3 significant figures gives 2, 3, and then 4. Now, since the next digit is 5, the 4 is rounded up toward 5. Our next question. It says Musa measured a table and recorded the length as what? 0.76 meters. That is correct to 2 decimal places. Which of these could be one of the actual reading Musa might have obtained before rounding? Now we want to check all of these. Which of them rounds to what? 0.76. That is what the question is about. So if you look at the very first one, it says what? A 0.766. Now, if you want to round 0.766 to 2 decimal places, it is actually going to be a 0.77. So that is certainly not the answer, because you'll be rounding up. 0.86 is already in 2 decimal places, so it maintains the 0.86. 0.754, we want to round it to 2 decimal places. This 4, which is our decider, is less than 5. Hence, we are going to keep the 0.75 as it is. Now, for the last one, 0.764. This decider is also less than 5. Hence, we will just keep the 0.76 as our what? Rounding. So our answer is D. And that is just it. Our next question says, what is the result of expressing this correct to 3 decimal places? So what are we correcting? That is a 745.9674. We want to correct this to 3 decimal places. So to 3 decimal places, we know this is our first decimal place, this is our second, and this is our third. Now, if we want to end over here, then we need to consider the decider. This decider is a weak decider, that is 4. Hence, it has no effect on the third decimal place. Hence, we are going to get a 745.967. And that is B. It says the fourth decimal digit is 4, which is less than 5. So the third digit, which is 7, remains unchanged. Question number 11. We've solved 10 questions so far. You can take a break and then you come so we continue. Okay, so welcome back. It says, if a rod, that is question number 11, if a rod in the multi-base material represents a what? A million, then how many rods are needed to make a flat? And a flat is actually 10 millions, you see. So this is just a repetition of all that we did previously. You would have to divide, you see. So in dividing, so knowing our rod is what? A million, and then our flat being what? Tens of millions. All we are going to do is to divide the number of flats by what we have for a rod. So dividing, we have all these zeros cancelling out these zeros, and this taking out this. Hence, we have 10 over 1. And 10 over 1 gives us what? A 10. So it simply implies that we need 10 rods to actually give us one of the what? Flats. You see, and that is 10. You see, since the flat is 10 million and the rod is 1 million, 10 rods are required to equal the value of one flat. Question number 12. It says to represent a 1 million Ghana cedi using only 50 Ghana cedis notes, how many notes are required? You see, so how do we go about this? We said earlier on that you divide the total amount, which in this case is the 1 million Ghana cedis, by the denomination. Our denomination here is the 50 cedis. You see, so doing that will simply mean divide your 1 million by what? 50. So how do we do that? This 0 cancels out to this 0. 5 into 10 twice. So we have 0, 0, 0, 0. And that gives us a 20,000. It simply means we need 20,000 notes of the 50 cedis to give us what? A million cedis. Our next question here says, which of the following numbers is exactly 500,000 less than what? 1,295,800,000. This here is a subtraction question, which simply means you should subtract 500,000 from what you have over here. So let's do our subtraction here. So using our vertical method of subtraction, which we have over here, 0 minus 0 gives us a 0, 0 minus 0 gives us a 0, all these gives us 0. Then we have 8 minus 5, which gives us a 3. These have nothing to subtract. So we have 5, then your 9, 2, and then 1. So it simply means our answer is 1,295,300,000, and that is D. You see. Question number 14. It says using skip count backwards. We are skip counting backwards in 250s from 1,000. What is the second number you would see? That is after the starting number. So our first point is what? Our first number is 1,000. Take note. It says what is the second number we will see? The first number we are going to say is 1,000. You see, then the second number would have to take out 250 from this. So 250 from 1,000 is going to give us what? A 750. So 750 is the second number we are going to see. So starting again, we have what? 1,000, which is the first number. Then the second number, which is what? 750. So our answer is 750. And the reason is starting at 1,000 and subtracting the interval 250 once leaves to what? 750. Our next question says we have to round this. That is 1,879,653 to the nearest 10,000 using the round off method. So this is our number here, and take note, it says we should round it off to the nearest 10,000. If it's 10,000 we are talking about, then what number do we have in the place of the tens of thousands? We have 7. 7 is in the place of the tens of thousands. Since we are rounding off, we need to consider the decider. In this case, the decider is what? 9. That is the digit in the thousands place. Now, if the decider is 5 or more, we say we round up. If the decider is 4 or less, we round down. So as we round up and down, all these other digits become 0. So you have 3 being 0, 0, 0. The 9 itself becomes 0. But it decides that we change the 7 to what? 8. Then we write the remaining digits as well. So this becomes our answer. That is 1,880,000. 1,880,000, as you can see. Our next question says, Which statement best defines round down? The round down concept. Which statement best defines it? So it says, considering the smaller of the two possible numbers. Is that true? That is true, but then let's read the remaining. It says, rounding to the larger. No, rounding to the larger is not rounding down. C says, changing all the digits to 0, regardless of their value. That isn't true. So rounding down, you don't change all the digits to 0. Then the third one says, always subtracting 1 from the target place value. No, we don't always subtract 1. Sometimes we even remain the same. So it is considering the smaller of the two possible numbers. We consider the smaller one. Yes. So that is rounding down. Question number 17. It says, if you round 2,846,655 down to the nearest 100,000, what is the result? So the number we have here is what? A 2,846,655. And take note, it says we have to round down to the nearest 100,000. What number do we have in place of the 100,000? This is what we have. It says we have to round what? Down. So rounding down, we always do what? We are going to maintain the digit we have here and change all these others to what? 0. You see? So rounding it down, we have our 2 and then maintain the 8. Then the remaining becomes 0. Rounding down always maintains the digit in question and changes the remaining. So we have a 0, 0, 0, 0, 0. And that is a 2,800,000. That is our B. Question number 18. Express this number to 4 significant figures. We are expressing the number to 4 significant figures. So let's first of all take note of the numbers. These actually, they are all non-zero digits, you see. And we know all non-zero digits are significant. But we want to end at the 4th significant figure. So this is our first significant figure, second, third, and then 4th. So we want to end just here. But we need to consider the decider. This number decides whether or not it remains the same or it is increased. Since it is 5 or more, it simply affects this, and hence it increases. So that we have our 8, 5, 7, then instead of 3, we change it to what? 4. And then change the remaining digits to a 0. You see? So that is C. 8, 5, 7, 400,000. Question number 19. It says, in this digit 7.021, why is this 0 considered significant? Remember, when it comes to the significance of 0, we said leading zeros are insignificant. Trailing zeros are significant if only they come after a decimal point. This we have here is not a leading 0, neither is it a trailing 0. It's a sandwiched 0. And for sandwiched 0, they are zeros, they are significant because they are trapped between non-zero digits. They have been contaminated with significance, hence they also become significant. So looking at our options here, it says because it is at the end of the number. That is not true. It is because it follows the decimal point. That is also not true. C says because it is trapped between non-zero digits. That is true. So 0 located between non-zero digits are always counted as significant. We either call them trapped zeros or sandwiched zeros. Question number 20. It says we have to round this digit to 6 significant figures. So the number we have is 84.40995000. We have to round it to just 6 significant figures. This is a significant, that is the first one. So non-zero, non-zero, they are all significant. This is also significant. This 0 is a trapped 0, hence it is significant. So far we've got 1, 2, 3, 4, Then this is a non-zero 5, and 6, which is also significant. But we will need to consider this to do the rounding. This digit we have here, that is our 5, affects the number that comes after it. It is going to let us round up. And rounding up simply means we are going to add 1 to this digit over here. If we add 1 to this digit, we get a 0, which is a 10. You see, so a 10, we write a 0. Then we add 1 to this because the 10 has rounded it to this. Hence, we also write another 0 and then bring the 1 here. So we have 1, and then we have our 4, then 0.84. This becomes our what? Rounding to 6 significant figures. So 1, 2, 3, 4, 5, 6. And that is what? B. You see? So let me actually take this again. The first 6 digits, that is 1, 2, 3, 4, 5, 6, 84.4099. They are all what? Significant. Now it has to do with our rounding will now depend on the next digit, which is 5. So it will cause this 9 to round up. If it rounds up, it becomes a 10. And we know something like this. If you are adding 1 to it, we are not going to write a 10. We are not going to write all the 10 down here, but rather write 0 and then add 1 here. You see, and this 9 also becomes 10. So we add 1 over here. That is how come this 0 has now become 1, and then we have a 4. Now, as to whether these are 6 significant figures as we wanted, you know, these zeros here are trailing zeros and they come after a decimal point. So they are also significant. That is why we can still confirm the fact that they are all significant, and hence we have what? 6 significant figures. This is question number 20. I would expect you to take a break so that we continue from question number 21. Take a break, stretch, and then freshen up a bit. Okay, so welcome back. Now we will be moving fast because we are actually doing the same thing, the same ideas, and then I do hope you are getting them. Question number 21 says if you round 486.3685 to the nearest tenth using the round up method, what is the result? So for what we have over here, it says we are rounding to the nearest tenth. Tenth is the first digit we have here. That is for decimal system. This is the tenth. And we are actually rounding up. So when it comes to rounding up, irrespective of the digits you have after it, you are always going to add 1 to it. You see, we are always going to add a 1. So it simply means we have 486 points. Instead of 3, it becomes what? A 4. As simple as that. So that is D. 22. It says express 745.9674 correct to 1 decimal place. 1 decimal place simply means we need to end right here. See, if you are ending right here, then we are going to get what? We need to consider the decider. The decider here is 6. So 6 adds 1 to what? 9. You see that it is going to add 1 to 9. And if it adds 1 to 9, this is going to be a 10. And we aren't going to write all the 10 there, but then we just write a 0, then round or bring up the 1 to the whole number. So that becomes a 6. Then we have 4, 7. So rounding this correct to the what? Correct to 1 decimal place, we are going to get is 746. That is A. You see, so it says the second decimal digit 6 is greater than 5, causing the 9 in the 10th place to round up, which in turn rounds up to the unit place. You see. Question 23 is in the number chart example. If you are looking at 3,185,500, which number is listed directly to its right? Now, we know on our number line, for instance, when we are listing numbers, as we move to the right, we have the greater numbers. You see, so if you look at all these options we have here, this is within the 2 millions, and it will definitely be at the left-hand side of our 3 million. So that is not going to be our answer. We have 1 million as well. It is also going to be at the left-hand side. This is a 4 million, which is going to be at the right-hand side. This is also a 3,600,000. It is also going to be at the right-hand side. But the question says, which number is listed directly to the right? So 4,183,000 would be to the further right than the 3,687,000. And that is going to be the answer. Question number 24 says, how do you write the number this in words? You see, this is how do you write this number in words? We know when it comes to writing numbers in words, you check the place value. So this year, it is in the millions. And how many millions do we have? We have 3 millions. These are thousands, and they are actually hundreds of thousands. So 687,000. Then we have a 500. So we have 3,687,500. And that is going to be our answer. You see. The next question says, which combination of 200 cedis, 100 cedis, and then 50 cedis notes correctly makes 1,000,000 cedis? And make sure each denomination is used. So we are going to make sure each and every denomination is used. Now, what that simply means is we are going to sum up all of this, and our answer is going to be the one that sums up to give us what? 1,000,000. If you look at this very first one here, it even doesn't obey the rule. It says ensuring each denomination is used. Right here, it is omitting the 100 cedis. And right here, it is also omitting the 50 cedis. So we are not even going to consider that. Let's look at the second one. So for this second one we have here, well, it tries its best to include all the denominations. So we have the 200, the 100, and then the 50. So as to whether it is true or not, we would have to do the multiplication and then sum them up. So we have 2 times 4, which gives us what? An 8. So we write all the zeros attached to it. So 0, 0, 0, and then a 0, 0. That is 800,000. Then we come to a 1 times 1, so plus 1. Then we add the zeros. So there are 5 zeros in total. Then plus 2 times 5, which also gives us a 10. Then we add the remaining zeros. So in actual sense, we want to add all of this using the vertical method. So as you can see, if we want to use this method and we want to add everything, we have all of these giving us what? Zeros. Then 8 plus 1 then gives us what? A 10. And that gives us 1,000,000 cedis. It simply means the B satisfies, and there's no need going to check for the remaining. You see. Question number 26. It says for the number 0.0605368, what is the result when rounded to the nearest thousandth? And I do expect that for these questions, you should even be conversant with them and then even not wait for my solution. Okay. So we are rounding to the nearest thousand. This is the 10th, and then this is the 100th, and then this is the 1000th. our decider here is 5 or more. Hence, we are going to end at the 0.06. Then instead of 0, we use what? 61, because our decider is going to round it up. So that is B. It says the digits to the 10,000 place is 5. So the 100 digit is rounded up toward 1. Question number 27. Musa's actual reading for a table was what? 0.758 meters. Now, if he rounds this to 2 decimal places, what value should he record? So if you're actually rounding this to 2 decimal places, this is our first decimal place and then our second decimal place. And if you want to end here, considering your decider, you are going to get a 0.7. Instead of 5, you have a 6, because the decider is 5 or more. Hence, we are going to add 1 to what? The 5, so that it becomes 6. So that is a C for correct answer. Question number 28. So for this particular example, it says, what is the correct way to model 5,560 using multiples of 200, 100, 50, and then a 10? So we have, since it has been modeled already, all you need to do is to evaluate and then see if you are going to get your 5,560. So we start with the first one. We have a 20 times 200, then plus a 10 times 100, plus 11 times a 50, and then plus a 1 times 10. So 2 times 200, we have 4, and then 0, 0, 0, plus. So this time around, since we'll be adding, let me just use the method right away. So plus 1 times 1 gives us a 1, then we add 3 zeros to it. So 1, 0, 0, 0. Then 11 times 5 gives us a 55. We have 55, then with our 0. And then we have a 1 times 10, which also gives us a 10. So we have our 10 this way. And all we want to do is to add everything down. So we have all the zeros giving us a 0. A 0 plus 5 plus 1 gives us a 6. Then 0 plus 0 plus 5 also gives us a 5. Then we have 4 plus 1 gives us what? Giving us a 5. So with this, I don't even think there's a need to check the remaining. So we choose our A, because when we evaluate it, we are able to match the question that was given us. Question number 29. It says, in this number, how many zeros are considered significant? Looking at the question, or looking at the number, it says in the number 0.0027357, how many of the zeros are considered significant? All the zeros here, well, if I've not missed any, all the zeros here are actually leading zeros. And we have said countless times that leading zeros are not significant. There is no other zero we have in here. So this 0 is not significant, this is not significant, and this is also not significant, because they are leading zeros. Easy. So we can say none of the zeros are significant. These all zeros in this number are leading zeros. And leading zeros are never significant. They are just placeholders. You see. Question number 30. It says, what relationship symbol correctly compares these two digits? So we are actually comparing. So we have said earlier on that if we want to compare digits, we need to first of all count the number of digits. So let's see if they are the same. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. They're actually the same, right? So we have 1, 3, 1, 3, 0, 0, 0, 0, 8, 5, 8, 5, 0, 0, 7, 0, 0, 7, 0, 0. They are the same. So it's just an equal to, since they are the same. So we would pause here Okay, I would advise that you pause on question number 30, walk around, stretch, then you come for us to continue. So, question number 31, it says, if 10 blocks make a billion, how many rods? And we are saying one rod is what? Just 1,000. So, how 1 million? Sorry. So, how many rods are required to model exactly one half of a billion? So, looking at what we have over here, here are the 10 blocks. And 10 blocks are giving us a billion. You see, then just one rod is 1 million. Now, what is half of a billion? Half of a billion is simply half of this 10 blocks. So half of a billion is actually 5 blocks. You see, so we are going to divide this by 2 and also divide this by 2. So we are going to say that half of a billion giving us what? A 500 million. You see, so if that is the case, we want to determine how many of these rods we have in here. And as we have always done, we divide. So I'm going to cancel out these 3 zeros and do same for what we have over here. And you realize that we have just 1 over what? 500. So it simply implies that 500 rods are required to model exactly one half of a billion. So let's choose that. Okay. Now question number 22. It says a bank needs to pay out 2,450,000,000 cedis using the largest possible denominations. If they use 10 million notes of 200 cedis, how much balance remains to be paid? So right here, our parameters we've been given are this. Amount to pay out, that is the 2,450,000,000. And then amount that has been paid out is 10 millions of 200 cedis. Now, if we are to multiply this, what are we going to get? So we have 1 times 2, which gives us a 2. Then we write all the zeros attached. So we have 0, 0, 0, then a 0. So after our calculation, we will realize that 2 billion has been paid. See, so with this, you can even look at it and tell what the difference is. If you have to pay 2,450,000,000, and you've actually just paid 2 billion, then you're actually left with 450 what million. D. As simple as that. Now, question number 33. It says in a sequence, skip counting by 125,000, starting from a billion. What is the fifth number in the sequence? Okay, so looking at this, we actually skip counting in what billions. And since we've not been told either forward or backwards, then the default is forward. So our first number I would mention in the sequence is the 1 billion. So after the 1 billion, we are going to add a 125,000 to it. So right here, let me just do my addition, 125,000. And if we add all this together, you know, these are all zeros we have here. So it's just going to be the same thing at this side. And then the 125 would follow. Now this becomes our second number in the skip count. So this is first, then the second. For the third one, we need to add a 125 again to it. So adding all of this together to give us the next number, we have 0 plus 0 giving us a 0. Then 5 plus 5, we have a 0 carry 1 giving us a 5. Then 1 plus 1, we have 2. With all these remaining just as they are. So with that, this becomes our third number. So with our third number now, we add the same digit, or the same number, sorry, to it. So let me just do that here. And what are we adding to it? We are adding the 125,000 to it. So we have our 125 here. Then I'm going to add all of this once again. So we still have our 0, 0, 0. And 0 plus 5 gives us a 5. Then 2 plus 5 gives us a 7. 2 plus 1, we have a 3. Then the remaining still are 0. So we have first, second, third, and this is our fourth one. We now add again the 1,205 to it. And the result of this becomes our answer. So we have all these 3 zeros remaining intact. Then we have 5 plus 5 giving us a 0. 7 plus 2, we are going to get another what? 0. And then 3 plus 1, we are going to get a 5 because of the rounding, you see. So a 0, 0, 0, and then 1. This here becomes our answer. So it is a 1,500,000. That is the result of our skip count. So the fifth number among these options, that is E. You see, so the trick is simple. Since you are skip counting is repeated addition. You keep adding the number you are skip counting by, and you'll be good to go. In our next question, that is question number 34. What does it say? It says, which of the following numbers would result in 0.5 when rounded to one significant figure? We are rounding to one significant figure. Our first number, we have 4.98. So 4.98, if we want to round this to one significant figure, this is the first significant figure. So we'll consider our decider. Our decider is a 9. And if it is 9, then we are going to round up. You see, if you are going to round up, then you are going to get a 5.0. That becomes the rounding to one significant figure. Let's try the remaining. If we're looking at the second one, if we actually want to round to one significant figure, that is 5.9. So our first significant figure is what? 5. And if you want to round it and then end right there, we look at our decider. This decider here is also 9. You see, so what it does is going to affect the 5 so that it becomes 6. We are rounding up so that we have a 0.6. That is to one significant figure. Then the next one, which is a 5.51. If you want to round that as well to one significant figure, this is the first significant figure. And the decider is what? 5. So you round up and that becomes 6. So that is to one significant figure. Then we have the 4.49. If we also want to round this to one significant figure, we are ending here. But then the decider is 4. And 4 is less than what the required value to round up. Hence, it still remains 4. That is in one significant figure. So our answer, as I have said, is what? The 4.98, because it is the only digit that rounds to 5 in one significant what figures. The next question, it says if a number x is rounded down to the nearest thousands, to get, so our number we are actually getting is what, a 45,000. That is after the round down. Which of these could be the original value of x? We are rounding down. Considering the first number, which is 44,000, if you want to round this down, you're rounding it down to the nearest thousands. If you look at the thousand here, well, this number is already in the nearest thousand, so you can't even round it up nor down, you see, because it's already in the nearest thousands. But if we consider 45,850, if you have to round this down, this is our decider. For rounding down, irrespective of the decider, we always change the remaining digits to 0. You see, so that is for rounding down. Hence, we have 4, 5, maintain the place value we are talking about, and then change all to 0. For the next one, which is 44,999. So as I've said, for rounding down, maintain the place value you are talking about. So we maintain 44 and change all the remaining to 0. The next one, which is 46001, rounding down to the nearest thousands. You maintain the thousand column, which is a 4, 6, and then change the remaining to 0. So among all of them, which actually gives us the 45,000? See, and that is the second one here, 45,850. Our next question says, how many significant figures are in this number we see over here? So we have a 0.0007 and then 0020. How many significant figures do we have? For this zeros, we call them leading zeros, and leading zeros are all not significant. Hence, there are 0 here. Then this is a non-zero digit. Non-zero digits are significant. So we have our first significant number. Then this 0 is also significant. This 0 is also significant. The reason being that it is a sandwiched 0. See, that is a trapped 0. A 0 between significant figures. And that makes it what? Significant. So we have 1, 2, 3, 4. And this last 0 we see here is a trailing 0. A trailing 0 that actually comes after our decimal place. So it is also significant. Hence, you have 1, 2, 3, 4, 5. There are 5 significant figures right there. Number 37 says, a measurement is recorded as 12.40. So 12.40 meters. Correct to 2 decimal places. So we have 2 decimal places here. What is the smallest possible actual value to have been before it could have been before rounding off? So we are going to round off all of these numbers. And we see among them the smallest one that actually gives us 12.40 when we round it off. The first one, we have 12.35. For 12.35, it is already in two decimal places. So since it is already in 2 decimal places, it is actually out. It wasn't even rounded. The second one, which is 12.39 meters, is also already in a 2 decimal places. The third one, which is a 12.401 meters, it is in a 3 decimal places. So if you want to round it to 2 decimal places, this decider is below 5 and it has no effect on what the nth or the place value we are considering or the number of decimal places. Hence we have 12.40. So this could be the number. But let's consider the next one, which is actually a 12.395. And mind you, this is also in 3 decimal places. So if you actually want to round it to 2 decimal places, that is to end here, then we have this decider, which is 5 or more. So we are going to add 1 to what we have here. And that alone will give us what? 10. If we put 10 here, we are just going to write 0 and then round the 1 over here. And that is going to give us a 12.40 meters as well. So if you have to compare this and then this, you realize that this one is smaller. And the question says, what is the smallest possible actual value it could have been before rounding off? So it could have been what? 12.39 meters. Question number 38. Express this number to 3 significant figures. So with this, all we need to do is to target the third significant figure and see if we are going to round off, that is up or down. So this is not significant, it's a leading 0, then we come to 4. 4 becomes our first significant figure, 5 becomes our second significant figure, and the 0 here is our third significant figure because it's a trapped 0. But we can't end here. We need to consider our decider. So we have a 0.045, then the 0 here becomes 1 because our decider is more than 5. It is more than 4. That is 5 or more. So our answer is 0.451. The next one says we have to round this number to the nearest thousands using the round up method. So you have 9. Now, if we are rounding up, we know we need to identify the place where we want to round to. It says nearest thousands. So this is our 1000 here. And the rule simply says, let's just change the remaining to 0. And since this round up, we'll need to add just 1 toward the 9. So 1 plus 9 gives us a 10. Write a 0 and then bring a 1 here. 1 plus this 9 also gives us a 10. We write a 0, then also bring a 1 here. This also gives us a 10, and then this also gives us a 10. So instead of rounding up to the nearest 1000, you see the result it has come to what give us. That is a 10 million. Because we kept carrying over the results. Question number 40. Which set of numbers is ordered correctly from the least to the greatest? So since it says from the least to the greatest, you are coming to look at all these numbers, the one that has the arrangement in the list from the least to the greatest. So for each and every one, we'll just look at the number of digits, you see, to compare and then know its weight. For the first one here, we have 3, 6, 9, we have 10 digits. This also has 10 digits. This also has a 10 digit. All the first digits are the same. For the second digits, this is a 0. This is also a 0, and then this is a 1. So it simply means this one is even greater than all of them. Now let's compare these two. So there's a 0 and then a 0 here. Well, there's a 0 and then there's a 1 here. So it also means that this one is greater than this. So I think the answer is just the A. But let's try and go through the remaining and see. These are also 10 digits and they all start with 2. Well, since it is the same number, the same set of numbers throughout, then I think the answer is just A and we can move on. Question number 41. At this point, move around for just a minute, and then you come a minute or two so that we go through this. So welcome back. Question number 41 says you have to model 8,400 using only flat. And it tells us that a flat is what? 100. And then a rod is a 10. Then a cube is 1. So we have 8,400 to model. And then it says if you use 80 flats, 35 rods, how many cubes are needed? So already we have gotten 80 of the flats already, and then 35 of the rods already. Now take note, a flat is 100 units. In actual sense, we have 80 times 100, then plus a rod is also 10 units. So 35 times a rod, which is what? 10. If you have to simplify, we have 8, then 0, 0, 0, plus 35, 350. If we add 800 to 350, we have 8,000 to 350, you have 8,350. But take note, it is an 8,400 we actually wanted to model, and not with a 350. So what we do is we are going to subtract 8,350 from 8,400. The remaining is what we would then need for what? The cube. So the cube covers the remaining. Doing that here, we have 8,400, then minus our 8,350. What does that give us? It gives us a 50. It simply means we need what? 50 cubes. You see, we know a cube is just a unit. So 50 of those cubes to actually complete our model. Question number 42. It says, what happens to the number if it is corrected to 0 decimal place? If you want to round to the 0 decimal place, simply means you actually want to round to the nearest ones. So since we want to end over here, then we consider our decider, which is 7. And we know if it is 5 or more, we round up. So all we need to do is to add 1 to 6. So that becomes what? The 4, 5, 7. And with this, we have no decimal place. So that is, it becomes 457. So take note. It says correcting to 0 decimal place is the same as rounding to the nearest whole number. We are rounding to the nearest whole number. So if we decide on where we have our first whole number, that is the digit here, after the decimal, that is before the decimal place, we then just go to the digit after the decimal place, which is our decider, and then we do the needful. Question number 43. In this number, which digit is the 10 billionth place? So with the digits we have here, we know these are the hundreds. Then we come to the thousands, the millions, and the billions. And our focus here is what? The billions. So this is the billions. This becomes the ones of billions, and then this becomes the tens of billions. So we actually have 5 in the 10 billion place. Easy. Okay. Question number 44. It says we have to round this digit to two significant figures. We have 0.00045, then 6, 7. If you want to round this to two significant figures, all these leading zeros are what? Not significant. So 0.00 then the 0 are not significant. Our first significant figure is the 4, followed by the 5, but we can't just write the 5 because the number that comes after it is 6, and 6 will cause us to round up. So we have 4, 6, and this becomes our rounding. So that is the C, which is 0.00046, as rounding this to two significant figures. Number 45. If you skip count by 50 millions, how many skips are needed to get from this digit, that is, to what? This digit. So what we actually have is what? 100 million, but we want to skip count and then get to a billion. The skip counting we are doing is actually in 50 what? 50 millions. So how do we go about this? First of all, we need to know the difference between these two digits. And then we'll get to know how many times of the 50 millions we need to cover that difference. If we are to subtract this from this using the vertical method, we know first of all that all these will keep giving us zeros. So the main deal is here. That is 10 minus 1, which gives us a 9. So that simply means that we need to skip count this in what? 50 millions consecutively till we cover this we have over here. So a simple way you can get the number of times is through division. So all we need to do is to divide this digit we have by this. The quotient then becomes what? The number of skips we need. So this is our number here, and then in dividing, all these cancel out all of this. This also cancels out this. Then we have the 0 taking out this 0. So it's now a matter of 90 divided by 5. So 5 divides itself once, and it divides 90, that is 18 times, because 5 times 18 gives us 90. So that simply means if you want to skip count by 50 millions, we need to skip count 15 times before we can get to this number over here. You see, so that is, we need to skip count 18 times before we can get to what? This number over here. So we have 18 skips, and it simply says the difference is, as we just did, then dividing this by this equals 18. Very simple. Question number 46. Now 46 says, which of these numbers has the same value when rounded to two significant figures and two decimal places? So we are taking the numbers, and what we want to do is we want to round to two decimal places and also round to two significant figures. Our first digit, or our first number, is what? 0.44. So for this first column, I'm going to do the two significant figures, and then right here I will do the two decimal places. So for two significant figures, these two digits are the only significant figures we have. So we have 0.44, And for 2 decimal place as well, there is nothing to round. So 0.44. Our next one is what? A 1.23. If you are to round this to 2 significant figures, remember this is significant. They are all non-zero digits and they are all significant. So we will need to end right here. And our decider here isn't even going to help. So we have 1.2. This is to 2 significant figures. But for the decimal place, it remains that is as it is. That is a 1.23. The next number was a 10.55. If we need it in 2 significant figures, we have 1 and then 2, but we can't end on the 0. So we need to round up so that it becomes what? A 1, 1. That is 11. So that is to 2 significant figures. But for 2 decimal places, it still remains as it is. Then for the very last one, which is a 0.045, if you want it in 2 significant figures, it also remains the same because the leading zeros we have there are not significant. Then for 2 decimal places, we have 0.05. The 4 becomes 5 because our decider is going to round it up. So among all these we have, which of them has both the significant figures and then the decimal place being the same? It is just the first one, that is a 0.44, and that becomes our answer. The next question says we have to express the sum of this and then this to the correct number of decimal places based on the least precise measurement. So before I explain what this least precise measurement is, let's quickly do the addition. So since there is sum means addition, we have 45, then 0.67. Wow, 67. Then we have 2.3. And we want to add these two. So we can simply add placeholders just to help us in our addition. So 20.30. If you are adding, you know, these are all placeholders. Even though this 0 here we say is significant, but then it doesn't affect the value of the calculation. So 7 plus 0 gives us what? 7. Then 6 plus 3 gives us a 9. And then we have 5 plus 2 giving us what? A 7. Then 4 plus 0 giving us a 4. So this becomes our answer after the what? The sum, the summation. Now it says we should correct it to the least precise. Now, the more decimal places you have, the more precise we want to get, you see. So by looking at the 2 measurements we were given, this first number, which is 45.67, was very, very precise. That is the highest precise one. This second one, which was just the 2.3, was the least precise one because they didn't give us any further decimal places. So it simply means we have to round this to 1 decimal place because it is the least precise number we were given. So rounding 47.97 to 1 decimal place, we want to end here. But then our decider is saying we should add 1 more to the 10th. So that it becomes what? A 40. Instead of 47, we are going to get a 48. Because if you have to add 1 to the 9, we get a 10. And then the 10 also carries that to the 7. So 48.0. We need the 0 to indicate our decimal place. You see, so we have 48.0 as you see right here. Question number 48. We have to round this to 4 significant figures. So the number is 1, 2, 3, 4, 5, 6, 7, and then 8. Well, we have the decimal point between 4 and 5. So I'm going to put that there. And we are rounding this to 4 significant figures. So to 4 significant figures, this is our first, second, third, then fourth. Then our decider is what? 5. So our decider is going to cause us to round up because it is 5. So we are getting a 1, 2, 3, then what? A 5. That becomes our rounding to the 4th significant figure. And that here is C. As simple as that. Question number 49. Now 49 says, if you round 0.00702 to 2 significant figures, what is the result? So what do we want to do here? We want to round this to 2 significant figures. All these leading zeros are insignificant. This is our first significant figure, and this is also our second significant figure. And we want to just end it right there. Now our decider here is less than the required value to round up. So in rounding to 2 significant figures, we are just going to get a 0.007 and then 0. That is to 2 significant figures. So that is our C. Question number 50. How many flats are needed to represent a quantity that is exactly double the value of 1 block? We know that our flat. So we know that our flat is what? A 10 million. And a block is 100 million. But what we actually want to model is what? Double of a block. So double of a block is then going to give us all of this times 2. So it is just a 200, and then we put our zeros there. So how many of this do we actually have in this? That is all the question is saying. And as we have done on countless occasions, we just know what we have to do. So all of these zeros, there are 5, there are 6. It takes out this. Then we have this also taking out this. What we do have left is what? 20. It simply means we need 20 flats to do that job for us. If you have stayed glued to your screen and then solved along with us even up to now, then you have actually done so well. There are 50 more questions we can answer to enhance our understanding, but I'll put a link of these questions in the comment section so that you try them on your own based on all that we've done so far to test your understanding as well. This is how Beyond Numbers, where we learn maths the easy way. In our next lesson, we'll be looking at the next substrand, and then we'll also solve 50 questions on it to enhance our understanding. I do hope this lesson was helpful. If this is your first time on this channel and you so do wish, you can choose to subscribe so that anytime I release a video, you'll be notified as well. Stay blessed and bye for now.